The office this evening looks like it's rehearsing for something that hasn't quite arrived. Papers have slid off the desk into loose spirals near the door. The blinds tap against the window in a restless rhythm, and the lamp over my case file sways just enough to make shadows spin on the walls. A fan in the corner keeps pushing little lines of dust and pen caps into narrow streaks, as if the room is trying to sketch its own wind field across the floor. I'm standing in the middle of it all, with a notebook in one hand and a mug cooling in the other, thinking about what it takes for a scene like this to tip from cluttered into truly torn apart. Welcome to Science to Sleep To. I'm Madeline Rowe, and this is Tornadoes for Sleep. For those who don't know, I'm an astrophysicist turned private eye, trading telescope time for case files, and tonight, a temporary seat at the severe storms desk. This investigation is a quiet one, filed under rotation and pressure, under long-lived thunderstorms that learn to organize themselves and sometimes, only briefly, draw a narrow column of wild wind down to the ground. So settle in, let the room feel a little wider and more like a calm night on the plains, and we'll open the file on tornadoes together, slowly, steadily, one calm page at a time. And one last thing before spinning off. If this slow dive into rotating storms helps you drift off, you might like to keep a few more case files on the shelf. If you're still awake later, you can tap subscribe or follow, so the next calm weather story is waiting for you on the nights you need it. No pressure at all, just another quiet tool for your sleep kit. Okay then, here we go. Somewhere out over the plains, or over a valley in New England, a thunderstorm is becoming something more. Not just a burst of rain and lightning, but a long-lived, rotating engine in the sky, a supercell. Most of the time, even these powerful storms come and go without a tornado. The air rises, the rain falls, the storm drifts away, and the landscape settles back into silence. But sometimes, near the ground, a compact vortex takes shape, a hidden rotation that tightens, stretches, and briefly anchors itself to the surface. That is the invisible vortex at the heart of tonight's case. Before we dive into the structure of these storms, a gentle note. If you find this kind of sleepy science helpful, you might like to subscribe or follow, so there is always another calm case file waiting for you on the nights you need it. You can decide that later. For now, all you have to do is rest and let the atmosphere do the work. We will walk slowly through how a supercell forms, how it organizes itself, how scientists think tornadoes develop in 4 broad stages, and how radar trucks, field campaigns, and global models are helping to refine that picture. Later, when the main story has settled in, we will simply stay with the atmosphere a little longer, letting it carry us through some quieter scenes that you can drift off to whenever you like. If you fall asleep at any point, that is not a problem, that is the whole point. To start, picture a wide, open landscape. The ground is flat or gently rolling. Fields, fences. A road that seems to stretch in a straight line until it dissolves into haze. The air near the surface is warm and humid. Higher up, the air is cooler and drier, and the winds above your head are stronger than the winds at your feet. These are the quiet ingredients for a thunderstorm: moisture, instability, and wind shear. Moisture provides the water vapor that will condense into cloud and rain. Instability means that if a parcel of air is nudged upward, it finds itself warmer than the air around it and keeps rising on its own. And vertical wind shear means the wind changes with height, in speed, in direction, or both. In an ordinary storm, warm air rises in a single pulse, condenses into towering cumulus, produces a burst of rain, and then collapses as the cooled air sinks back down. The updraft and the downdraft overlap. The storm chokes on its own rain-cooled air, and it fades away. A supercell is what happens when the wind shear is strong enough to keep that from happening. Instead of a rising bubble that quickly snuffs itself out, you get a storm that reorganizes the air around it. The updraft leans, the downdraft is pushed to one side. Inflow, updraft, and outflow separate into distinct regions. And the storm can persist for hours. Let us linger for a moment on those ingredients. Moisture is easy. You can feel it. A heavy, humid air that clings to the skin and makes leaves droop. Instability is more abstract. It is a measure of how much energy is stored in the vertical temperature profile of the atmosphere. Meteorologists often summarize it in a single number called CAPE, convective available potential energy. High CAPE means air parcels have a lot of potential energy to convert into upward motion once they start rising. Wind shear is the quiet sculptor in this story. Near the surface, the wind might be from the south. A little higher, it veers to the southwest. Higher still, it might blow strongly from the west. As you climb through the atmosphere, the wind not only speeds up, it rotates. This layered flow contains a reservoir of horizontal spin, invisible tubes of vorticity lying almost parallel to the ground. When a strong rising updraft taps into that layered wind, it can tilt those horizontal tubes of spin into the vertical. A rotating updraft forms. Meteorologists call it a mesocyclone. It is broad, often several kilometers across, and it can persist as long as the storm has access to warm, moist inflow and adequate shear. Not every environment with moisture and instability produces a supercell. You need a particular balance. Too little shear and storms pulse and collapse. Too much shear with weak instability, and the air never rises strongly enough to condense into deep convection. Supercells sit in the sweet spot. Strong instability, substantial low level and deep layer shear, and enough moisture to sustain a tall tower of cloud. Now that the ingredients are on the table, we can let the storm take shape. Let us build a mental cross-section of a classic supercell. Start with the updraft, a column of rising air that can extend 15 kilometers or more above the ground. At its top, where it punches into the stable layer of the upper troposphere, the cloud can briefly overshoot, forming a dome above the anvil. That is the storm's head. Spreading out from that head is the anvil. A broad, flat layer of ice cloud that fans downwind, carried by strong upper-level winds. Beneath the anvil, the storm's main body hangs as a tower of darker cloud. Beneath that, near the ground, the storm's internal regions are arranged like parts of a machine. On the forward flank, downwind of the updraft, rain and hail fall into the inflow. This forward flank downdraft carries cooled, rain-chilled air toward the surface and away from the core. On the rear flank, wrapping around the backside of the mesocyclone, another downdraft descends. It often brings drier air from mid-levels and can be relatively warm or cool depending on the storm. These downdrafts are important. They help organize the near-surface flow, and they are central to the modern picture of how tornadoes form. Radar images show this structure in abstract. A classic supercell may display a hook-shaped echo on its southwest flank, where precipitation wraps around the mesocyclone, inflow notches, weak echo regions where air is rising too quickly for many raindrops to remain. All of these features are clues. They tell forecasters that the storm is organised, rotating, and potentially capable of producing a tornado. But it is important to say this clearly. Most supercells do not produce a tornado at the surface. Many show strong rotation aloft. Many develop dramatic cloud features. Yet the necessary chain of events near the ground never quite clicks into place. Tonight, we are interested in those chains of events. The steps between a rotating storm and a tornado that actually touches down. Over the last several decades, field campaigns and high-resolution computer simulations have converged on a broad, four-stage picture of how many supercell tornadoes form. It is not the only path. Real storms are messy. But this scheme is a useful map. In the first stage, the storm's updraft develops a broad, persistent rotation. As inflow rises into the storm, horizontal tubes of spin from the environmental shear are tilted upright and stretched. The result is a column of cyclonic vorticity several kilometers across and extending through much of the storm's depth. This mesocyclone can be detected by Doppler radar as a velocity couplet. One side of the beam shows inbound velocities, the other shows outbound. The radar is essentially seeing air at different parts of the rotating column, moving toward and away from the radar. A mesocyclone is a sign of an organised, potentially severe storm. But by itself, it is not a tornado. It is broad. Its winds are strongest aloft, and its circulation often weakens as you move towards the ground. Closer to the surface, a different process unfolds. As downdrafts descend and spread, they can create sharp horizontal gradients in temperature and density. These baroclinic zones are places where vorticity can be generated. In simple terms, when cool, dense air slumps next to warmer, lighter air, and the pressure field adjusts, small regions of spin can appear. Near the edges of the forward flank and rear flank downdrafts, these processes create scattered patches and filaments of vertical vorticity near the surface. They are not yet part of a single, coherent vortex. Think of them as swirling hints, eddies and streaks of spin, roughly aligned with the mesocyclone, but still disorganized. As the storm evolves, the flow near the surface can begin to converge. Air near the ground is drawn inward toward the base of the mesocyclone. As it does, some of those scattered patches of vorticity are swept together. They merge, intensify, and begin to form a more continuous circulation. At the same time, upward accelerations in the low-level updraft begin to stretch the vortex. In fluid dynamics, stretching a column of rotating air tends to increase its spin, much like a figure skater pulling their arms inward during a spin. The vortex narrows, rotates faster, and focuses more strongly near the ground. This stage is delicate. Many things can halt it. If the cold pool produced by the downdrafts is too dense, it may undercut the inflow and prevent air from rising near the surface. If the vortex is displaced too far from the strongest updraft, it may not be stretched enough to intensify. Competing eddies can disrupt the flow, or the storm's own structure can change faster than the vortex can organize. This is one reason why so many supercells with strong rotation aloft never produce a tornado. When things do come together, a compact tornado vortex forms near the surface. Air at low levels flows inward toward the vortex, then rapidly turns upward. This pattern is sometimes called an in and up flow. just above the ground, a region called the corner flow region marks the transition from mostly horizontal inflow to mostly vertical ascent. Observations and simulations both suggest that, in many cases, the strongest intensification of the tornado circulation actually begins very low, near the surface, and then grows upward. The visible condensation funnel can give the opposite impression because it usually descends from the cloud base. But the pressure drop and the strongest winds may first lock in at the ground, then connect upward as the vortex matures. From the point of view of a forecaster, this multi-stage picture is a way to structure uncertainty. You might see a strong mesocyclone aloft, broad hints of near-surface vorticity, but still be waiting for the final stages to unfold. Warning decisions often have to be made while the system is balanced on that edge, before it is clear whether a tornado will in fact form. To move from conceptual picture to concrete numbers, researchers have spent years driving towards storms instead of away from them. Mobile Doppler radars, mounted on trucks, can park within a few kilometers of a tornado and scan the winds with fine resolution. These campaigns have built up a catalogue of three-dimensional wind fields in supercell tornadoes. When scientists stack these observations together, a few patterns emerge. Many observed supercell tornadoes have peak winds in the range you would associate with EF2 or EF3 damage. In metric terms, that is on the order of 60 meters per second, give or take. Strong, but not the absolute upper limit of what is physically possible. However, a significant minority of these tornadoes show winds that would be capable of EF4 or even EF5 damage if they happen to strike sturdy, well-constructed buildings. The fraction of storms in this category is higher in the radar data than in traditional damage-based statistics. That is partly because many of the strongest tornadoes in the radar dataset occurred in rural areas, where there were few structures to reveal the true peak winds. The radar data also show that many supercell tornadoes are wider than the narrow funnels that come to mind from movies or photographs. Median diameters of a few hundred meters are common, and a notable fraction extend beyond 1 kilometer across at the surface. The condensation funnel you see is only part of the story. The wind field and the vortex circulation can extend well beyond the visible cloud. For our purposes tonight, the important point is not the exact numbers. It is the way the atmosphere tends to use the same basic structures again and again. A rotating updraft, downdrafts that organize the near-surface flow, vortex patches that merge and intensify, and a compact in and up flow that briefly ties it all together. Supercells are often associated with the open plains, but they can also form over more complex terrain. One well-studied example is a long-lived supercell that crossed parts of New York and Massachusetts in late May of 1995. Along its path, the storm produced a violent tornado near the town of Great Barrington. The event is notable not just for its intensity, but for the way terrain and local flow patterns played into its history. As the storm moved eastward off higher ground into a broad river valley, the mesocyclone strengthened. The lower level winds in the valley were channeled along the river, enhancing shear near the surface. This created a more favourable environment for the development of strong, low-level rotation beneath the existing mesocyclone. Farther along its path, as the storm climbed back onto higher terrain, the rotation weakened at times, then intensified again as the storm descended into the next valley. The tornado's path broadened and narrowed, curved gently, and responded to subtle changes in the flow as it crossed ridges and river corridors. The details of that single event could fill their own episode. For our sleepy purposes, the main takeaway is simple. Even when the large-scale ingredients are in place, local terrain, valleys, and hills can nudge the low-level wind field just enough to encourage or discourage tornado formation. Prediction lives in that delicate balance. Until recently, the idea of modelling an entire planet's atmosphere at the resolution needed to resolve individual thunderstorms would have sounded like science fiction. But advances in computing power and model design have brought that idea closer. Some modern global models can now run with grid sizes of just a kilometre or less over parts of the globe. That is fine enough for deep convection to arise explicitly, without relying on the old approximations that treat storms as unresolved parameterizations. When these models are run in idealized setups, with warm oceans providing moisture and rotating planets setting the large-scale flow, supercells and tornado-like vortices can appear spontaneously. They are not perfect replicas of real storms. The vortices in these models tend to be broader and weaker than the most intense observed tornadoes, because even a kilometre-scale grid cannot capture every detail near the surface. But the basic dynamics look familiar. In the model output, you can see rotating updrafts forming in environments with strong shear. You can trace how horizontal vorticity is tilted and stretched into vertical vorticity. And you can follow how downdrafts generate new vorticity near the ground, which then feeds into tornado-like circulations. It is the same story, but now embedded in the broader context of planetary waves and jet streams. To diagnose these processes, researchers sometimes go straight to the governing equations. The vertical vorticity equation tracks how rotation about a vertical axis changes with time. It contains terms for stretching, tilting, and the generation of vorticity by horizontal density gradients. By computing each term in the model, scientists can see which ones dominate in different parts of the storm. It is a bit like an accountant checking which parts of a budget are driving the changes in a balance. For us, lying in the dark, listening to this, the details matter less than the broad message. Even in complex simulations covering an entire globe, supercells arise from the same basic ingredients and processes. The atmosphere reuses its favourite patterns, over and over again. Putting all of this together, forecasters blend several kinds of information. Conceptual models, like the multi-stage scheme for tornadogenesis, observations from Doppler radar networks, satellite imagery, lightning sensors, and mobile campaigns, and numerical model guidance from regional ensembles to global storm resolving simulations. Even with all of that, tornado prediction is inherently probabilistic. Slight changes in the timing of a boundary, the exact placement of a downdraft, or the subtle structure of the cold pool can make the difference between a strong tornado and none at all. The atmosphere at these scales is sensitive, chaotic, and in many ways irreducibly uncertain. From a human perspective, that uncertainty is challenging. Warning too often can desensitize people. Warning too little can leave communities exposed. The research we have been talking about tonight helps sharpen that balance. It gives forecasters better tools to judge which storms are most likely to produce a tornado, and when. From a sleepy perspective, there is something almost comforting about the idea that even the most intense local weather is part of a larger pattern. A single supercell is one node in the vast network of atmospheric motions. A brief, organized expression of energy in a fluid that is always in motion. As you lie here listening, the same physics is at work all around the planet. Air rising, air sinking. layers sliding past one another in enormous, gentle spirals. If you are already drifting off, you can let the rest of the episode wash over you. From here on, we can stay with the storms in a more relaxed way. Not to add new facts, just to wander through a few slow scenes together. Sometimes, instead of being out under the storm, I like to think of sitting with the people who watch it from a distance. Picture a small forecast office on a quiet night. Low lights, rows of monitors glowing in soft blues and greens, radar loops playing on one screen, satellite images drifting slowly on another. Outside, the wind might be steady or completely calm. Inside, the only motion is in the pixels. On the radar display, a supercell rotates in place like a living glyph. The reflectivity field shows the familiar shapes. A hook wrapping around the southern flank, a forward flank echo stretching away downwind. Small notches where inflow pushes into the storm. Overlaid on that, the velocity field trips between colours that mean toward and away. The mesocyclone shows up as a tight couplet, one side pulling, the other pushing. The people in the room talk quietly. They are not narrating for anyone but themselves, just small updates, a note that the low-level jet is strengthening, that the boundary to the south is lifting slowly northward, that the next radar scan will catch the storm right as it crosses a county line. Every few minutes, a fresh sweep appears. The storm has inched eastward. The couplet has tightened or broadened. A new appendage of reflectivity has appeared, or an old one has faded away. Each scan is a frozen frame in a slow dance. In one corner of the room, a desk holds printouts of hodographs, curves that show how the wind changes with height. Near the surface, the line is short and points roughly from the south. Higher up, it curves and lengthens towards the west. The shape of that curve tells you how much horizontal vorticity the environment holds, and how easily it might be tilted and stretched into a mesocyclone. To a sleepy mind, the hodograph is just another quiet spiral, a thin ink trace of the same motion playing out on the radar screen. On another desk, a coffee mug sits half finished, cooling slowly. Someone has put a sticky note next to it with a quick sketch of the storm's path, a line across a map, a few towns circled, a short list of times when the storm is expected to be near each one based on its present motion. Behind those numbers is a whole stack of physics. But on the page it looks simple, a few names, a few estimates. As you sit with this scene, the main feeling is one of contained stillness. The atmosphere is doing something intricate and energetic a few counties away. But in the office, the chairs do not move. The keyboards do not rattle. The loudest sound is the soft hum of ventilation and the occasional rustle of paper. Eventually, the storm begins to weaken. The mesocyclone broadens. The inflow cools. The hook echo smears out into a more ordinary rainfield. On the velocity display, the tight couplet relaxes. Inbound and outbound blur back toward neutral shades. A forecaster reaches forward and clicks a few buttons. Warnings are trimmed or allowed to expire. Notes are added to a log. There is no applause when the storm decays, just a quiet sense that the atmosphere has finished one of its more elaborate sentences. You can let that sense of distance and calm seep into your own breathing. The knowledge that somewhere storms are spinning, and somewhere else people are watching them carefully. But right here, in this moment, there is only you. A body at rest, in a quiet room, listening to the story of motions far away. As the radar loops on, you can let the view drift back down to the ground again. Think of a single supercell and let time slow down around it. At first, it is only a budding tower in a field of cumulus, a slightly taller cloud in a sky full of small, puffy forms. The air beneath it is rich with moisture. The temperature profile is primed for deep convection, and the wind profile has that subtle twist with height. The young updraft grows, reaches higher, starts to feel the shear more strongly. Near the surface, the wind is gentle and warm. Higher up, it is stronger and from a different direction. Horizontal tubes of spin lie stacked in the flow. The rising air begins to tilt them. Turning sideways, whirlpools into the seeds of a vertical rotation. Minutes pass. The tower deepens. The first heavy drops begin to fall on the forward side. A small core of rain and hail develops. At the same time, the updraft leans downwind. It no longer sits directly on top of the downdraft. The storm starts to separate its own moving parts. As the separation improves, the updraft can breathe more freely. It ingests warm, moist inflow without immediately choking on its own rain. The downdraft, in turn, can spill out and spread without cutting off the rising plume. The storm becomes more like a machine and less like a simple bubble. Now the rotation in the updraft strengthens. What was a gentle spin becomes a defined mesocyclone. On radar, the velocity couplet tightens. In the cloud, you might see subtle bands or striations, indicators that air is not just going up and down, but also round and round. Downdrafts descend on the storm's flanks. Air that has given up some of its heat sinks toward the ground. On the forward flank, cool rain-soaked outflow pushes ahead. On the rear flank, drier air wraps around the rotating updraft. At the edges where these pools of air meet the inflow, baroclinic zones form. Little factories of vorticity along the gust fronts. Near the surface, patches of spin collect. Some deepen and fade, some stretch and tighten. The low-level flow has to thread its way through pockets of cool, dense air and tongues of warm inflow. Small differences in that pattern determine whether the storm will remain only a rotating tower, or briefly gather itself into something more focused near the ground. For a while, everything balances on that knife edge. You can almost feel the storm thinking about what to do. The mesocyclone is strong aloft. The downdrafts are organised. The vorticity field near the surface is rich. And yet, nothing is inevitable. A tiny shift in the gust front. A slight change in the inflow direction. The weakening of an updraft pulse at just the wrong moment. Any of these can lead to a storm that simply remains a supercell and nothing more. Or, in a smaller subset of cases, the flow will converge just right. Vortex patches merge, stretching dominates over disruption, and a compact near-surface vortex forms. For a short time, the storm holds that tighter structure. Then, as inflow cools or the environment changes, it relaxes again. The tight coil unwinds. The mesocyclone weakens. Rain spreads out. The storm devolves into a broader region of showers and ordinary thunder. Seen at this slow pace, with the sound turned almost all the way down, there is no drama, just a process. A series of quiet decisions made by air parcels following the rules of fluid dynamics. Let that sense of process be a backdrop for your own settling. Just as storms build, mature, and decay, your thoughts can crest and fade. Moving toward rest without needing to force anything, you can bring the focus back even closer now, away from storms and screens and models, all the way to this room, to your own body. Think of yourself as another vertical profile in the atmosphere, a column with gentle layers from head to toe. The top of the column is your scalp and forehead, the place where so many thoughts and forecasts tend to swirl. You can let that layer be like the outflow anvil of a storm, broad, thin, spreading outward, nothing pressing down. Let the muscles around your forehead smooth out. Let your eyes rest in their sockets, not needing to track anything. Below that is the layer of your jaw and throat. This is where words live. Calls to action, warnings, explanations. You do not need any of those right now. Let your jaw soften. Let your tongue rest comfortably, the way the air rests in a calm inflow layer when a storm has finally moved on. Then there is the layer of your chest, a place where updrafts and downdrafts can feel like they live. Breath enters, breath leaves. You do not need to change the rhythm. Just notice that each inhale is a small, gentle, rising motion. Each exhale is a quiet descent. Nothing forced, nothing dramatic. The circulation of a storm slowed down to the pace of a sleeping person. Further down, your abdomen and back form another layer. These are the regions that often hold the invisible shear of your day. Twists and tensions you pick up from trying to move in many directions at once. For a moment, give this layer permission to stop organizing itself. Muscles can release a little. The weight of your body can be handed off to whatever surface is supporting you. You are the air parcel that no longer has to rise. Your legs and feet form the near surface layer of this personal atmosphere, where you make contact with the ground, where forces are transferred between you and the planet. Tonight, those forces are simple. Gravity, support, no need to run, no need to anchor anything against the wind. You can let your feet and toes be completely still, like instruments bolted to the ground on a calm, clear night. Taken together, all these layers make one column, quietly stable, not rapidly overturning, not reaching for any new equilibrium, just sitting in a comfortable one. As you rest here, the world of storms and vortices can stay in the background, out over the plains, on a radar screen, in a research paper or a model run, far from this room, where your only job is to be another part of the atmosphere at rest. Thoughts may still drift through, but they can behave like high clouds on a gentle jet stream, passing overhead, not needing your full attention. The physics will go on without you. The atmosphere will continue to solve its equations. For now, you can simply lie here. Feel the weight of your body, the softness of your breathing, and the quiet knowledge that even the most complex storms grow out of simple rules. The same basic laws that hold everything in place while you fall asleep. If you're still awake, you can let your awareness lift back out of your own layers and settle beneath a single storm again, as a quiet observer moving through the landscape beneath a classic supercell. The road ahead is straight. The fields on either side are brushed by a steady southerly wind. Above the horizon, a single towering storm dominates the sky. From a distance, the storm looks like a rotating sculpture carved from cloud. The anvil stretches out ahead of the storm, a smooth canopy of ice cloud that fades gradually into thinner cirrus. Beneath it, the main updraft tower rises in a textured column. On its downstream side, sheets of rain and hail fall in a slightly translucent curtain. On the updraft side, the base of the cloud is darker and more complex. Bands and striations hint at the storm's slow rotation. As you drift closer in this mental fly-through, you can sense the inflow at the surface. Warm, moist air is being drawn toward the storm. Grasses lean in the wind. Dust lifts in subtle streaks. The air feels slightly cooler in the storm's shadow, but still rich with moisture. Beneath the main updraft, a broad region of weak echo on radar corresponds to air that is rising too quickly for much precipitation to accumulate. Visually, it appears as a darker, slightly sculpted cloud base. Underneath this base, a rounded lowering may mark the area of strongest rotation, where the mesocyclone dips closer to the ground. Even here, the motion is slow on human timescales. The whole storm takes several minutes to complete a broad rotation. You float upward now, through the inflow layer and into the updraft itself. The air cools as it rises and expands. Water vapor condenses into cloud droplets. Latent heat is released, fueling further ascent. Around you, narrow columns of rising air weave together into a broader, rotating structure. Higher still, ice crystals begin to form. The updraft carries them upward and then out into the anvil. Suspended there, they drift slowly downwind, creating thin veils and streaks that gradually fall out as virga. From this vantage point, you can see the curvature of the storm's anvil, and far below, the soft pattern of rain curtains sweeping across the surface. As you drift back down, you pass through the forward flank. Here the air is cooler, rain-filled. Drops splash against the ground in countless small impacts, each one a tiny transfer of momentum from sky to surface. Beneath the rain, the cold pool spreads outward, its leading edge marked by a subtle wind shift and a drop in temperature. Then you move through the rear flank, where drier air descends. Sometimes this rear flank downdraft is slightly warmer, sometimes cooler, depending on the storm's microphysics and environment. Its outflow wraps around the mesocyclone, shaping the low-level vorticity field. To your sleepy mind, it is just another layer in the storm's structure, another ring in the rotating sculpture. You float back to the surface now, standing on the quiet road as the storm glides past in the middle distance. Lightning flickers occasionally within the cloud. Thunder rolls softly, more felt than heard. The wind eases, and the storm drifts away into the night. As that storm fades, you find yourself walking instead of gliding, tracing a path along a valley where a supercell once travelled. The event is in the past. The sky above you is calm. You are simply using the landscape as a map to think about how air flowed during the storm. The valley floor is relatively flat. To either side, wooded hills rise in gentle slopes. A river follows the low ground, winding its way between towns and fields. On the day of the storm, low-level winds were guided along this river corridor, channeled by the terrain, slightly strengthened by the narrowing of the valley. As you walk, you can picture how those valley-guided winds fed into the base of the supercell's mesocyclone, how the enhanced shear near the surface may have helped focus vorticity into a more compact circulation. At certain points along the path, where the valley bends or widens, you pause. Here, the storm might have briefly lost that extra support. Its rotation at the surface might have weakened or shifted. You are not reconstructing every detail, just appreciating that even small changes in terrain can nudge the flow. Farther along, you climb a gentle hill. From the crest, you can see where the valley opens out. On the day of the storm, the supercell would have encountered a slightly different environment here. Less channeled flow, perhaps a different temperature profile near the surface. Those subtle shifts can influence whether the low-level vortex strengthens or weakens. You descend again, passing through areas where the path is lined with mature trees. Their trunks are straight, their canopies full. The present-day scene is peaceful. Bird song, distant traffic, a breeze through leaves. The violent part of the event is not something you see. Only the memory of airflows is of interest here. As you finish the walk, you arrive back at the river. The water slides by slowly. Surface ripples trace the direction of the current. In your mind, you link this gentle flow to the invisible currents that once threaded the valley during the storm. Both are examples of fluids responding to boundaries, channeled, guided, shaped by the terrain they move through. When the air is quiet and only traces are left behind, another kind of work begins. Not under the storm, but after it. A slow walk along the path where the winds once were. In one version of this story, you are not alone on that riverbank. You are walking with a small survey team. Clipboards, cameras, measuring tapes looped over shoulders. Their job is to read what the air has written on the landscape, to turn patterns in branches and boards back into an estimate of wind. They move slowly, noticing details that anyone else might miss. A tree bent but not snapped. Another twisted at the base. One uprooted and turned, each trunk pointing a slightly different way. Together, they sketch out the shape of the near surface flow that passed here. The enhanced Fujita scale, the EF scale, is their quiet translation tool. It does not measure wind directly. It uses damage as a proxy. Different kinds of structures, different types of vegetation. Each has a set of expected responses at different wind speeds. Surveyors walk through what the storm has touched and match what they see to those expectations. A lightly damaged shed might point to one range of wind speeds, a snapped, healthy tree trunk to another, a narrow streak where debris is swept mostly one way, then suddenly another streak where the pattern curves. Signs that the vortex's wind field was not uniform, that it had an inner structure with gradients and asymmetries. To the team, this is less about drama and more about careful classification. They are building a record, a line in a database that will later read something like path length, maximum width, estimated peak intensity. Maybe a short note about terrain, or about how the circulation strengthened or weakened along the way. Over the years, radar-based studies have shown that some of these events contained winds stronger and wider than the damage might suggest, especially in rural areas where there are few sturdy structures to sample the highest velocities. The surveyors know that what they see is a lower bound, that the atmosphere does not always leave an easy signature. Still, the EF scale gives a common language, a way to compare one event with another, across decades, across regions. As you walk with them, you can feel how methodical it is. No rushing, just step by step, feature by feature. A broken branch here, a scoured patch of soil there, faint arcs in the grass where something light went sliding. All of it goes into the mental picture of how the vortex sat on the landscape. Eventually, the team reaches the point where the path thins and fades. The signatures become lighter, a few scattered branches, a fence post leaning a little more than its neighbours. Then, nothing unusual at all. Somewhere just upstream of that point, the vortex lost its structure. The in and up flow relaxed. The near-surface winds dropped below the threshold where they could leave marks like these. Someone notes the end point, jots down a set of coordinates, draws a small symbol on a paper map. Later, that line will join others, a collection of paths that arc and intersect and parallel one another across a region. You can picture that map now. A large sheet pinned to a wall in a quiet back room. Counties outlined in thin ink. Rivers picked out in a slightly darker shade. Across this base layer, paths from many years lie stacked. Some short, some long, some almost straight, others with gentle curves. Each one a trace of a single evening or afternoon when a storm organised itself just so. Looking at such a map is a bit like looking at a star chart. Your eye begins to connect the lines, to see clusters where paths have overlapped. Regions where, over decades, conditions have been more favourable for these kinds of storms. Other regions where such tracks are rare, not impossible, just less common in the long statistics. Climatologists take those records and turn them into smooth fields, grids of estimated frequency, maps that say, here, an event like this happens on average once in so many years. Here, it is a little more likely. Here, a little less. The underlying physics is the same. Moisture, instability, shear. But the large-scale patterns of jet streams and boundaries and land-sea contrasts give some places more opportunities than others. For a forecaster, those maps are context, not destiny. They know that on any given day, the atmosphere can surprise. Local ingredients can line up in unexpected ways, but the long-term patterns still help. They tell you where to be especially alert when a certain kind of setup appears on a model run. For you, standing in front of that wall, the effect can be strangely calming. Each line is an intense event, but taken together, they become a pattern, a texture laid over the land. Evidence that, even in its most concentrated expressions, the atmosphere is still part of a larger statistical story. You might trace one path with your fingertip, following it from its beginning in one county to its fading end in the next, then step back and let your eyes relax. Let the individual lines blur, so that you see only regions of more and less, a soft, abstract shading of risk and quiet over the map. The paper itself has its own small history, pinholes where it has been moved, slight fading at the edges, little wrinkles where someone pressed too hard with a pen. The map is not just about storms. It is about years of people watching them, recording, updating, adding new paths when they appear, leaving blank space when seasons pass quietly. In a nearby drawer, there are folders of sketches and notes from individual surveys, measurements of treefall angles, photographs of subtle marks in soil, diagrams of how the circulation interacted with a hill or a river. All those small human observations are the bridge between what the storms did and the numbers that end up in a dataset. You could stay in this records room for a long time without anything changing. The air is still. The only movement is the occasional turning of a page. The atmosphere outside will do what it does, forming and unforming storms according to the same rules, sometimes leaving another line to add to the map, sometimes not. As you step away from the wall, you carry with you the sense that even the most focused events have a place in a broader picture. Individual paths, long-term patterns, human eyes and instruments trying to knit them together, with that feeling in the background, that blend of detail and overview. You can let the scene soften around the edges again, the shelves of folders, the maps, the quiet floor. All of it can fade gently, like radar echoes drifting off a screen. The scene shifts again, and you are back in a quiet office. A large monitor shows a coloured map of vertical vorticity in a modelled supercell. Reds and purples mark regions of cyclonic rotation. Blues and greens mark anticyclonic areas. The entire pattern is slowly evolving, frame by frame. On another part of the screen, the vertical vorticity equation is written out. Without going into symbols, you can think of it as a balance between several processes. One term represents stretching. When a column of air shrinks in radius and grows taller, its spin intensifies. Another term represents tilting, when horizontal spin is turned upright by vertical motions. Yet another represents the generation of vorticity by horizontal density gradients, such as along the edges of cold pools. The scientist at the desk has decomposed the model fields into each of these contributions. On the screen, you can cycle through maps showing where stretching is strongest, where tilting dominates, and where baroclinic generation plays a leading role. In some parts of the storm, stretching is the main driver. In others, tilting builds new rotation from horizontal shear. Along gust fronts, baroclinic terms light up, marking places where new vortex patches may form. Watching the patterns change slowly in time, you can see how these processes conspire to create and maintain the mesocyclone and any tornado like vortices. Early in the storm's life, tilting is strong near the updraft, as the environmental shear is pulled upright. Later, once a strong rotating column is established, stretching becomes more important. Near the surface, along the gust front, baroclinic generation pulses as downdrafts interact with the inflow. To your sleepy mind, the details blur into a single impression, a sense that even complex, chaotic flows can be described by a small set of recurring operations. Stretch, tilt, generate, advect, move rotation from place to place, enhance it, or weaken it. Eventually the scientist turns off the monitor. The room returns to darkness. And the equations, like the storms they describe, continue quietly in the background of the atmosphere, whether anyone is watching or not. For one last shift in scale, picture a virtual Earth, not a photograph, but a globe rendered from a global model. The oceans are shaded in gradients that reflect sea surface temperature. The continents are outlined, and above them, layers of cloud are represented by translucent textures. At this resolution, you can see individual thunderstorms in the tropics, lines of storms along frontal boundaries, and in a focused region of the grid, detailed supercell structures with rotating updrafts. Tornado-like vortices appear as small, intense knots of vorticity near the ground. Within the model, all of these features arise because the equations allow them to. There is no separate instruction telling the model to include a tornado. It simply solves the fluid equations at high enough resolution that such structures can emerge on their own. Now the model is rerun under slightly different global conditions. Perhaps the average sea surface temperature is warmer, or the distribution of land and ocean is adjusted in an idealized way. The model produces a different pattern of storms. In some regions, supercells are a little more frequent. In others, they are less common. The global statistics of severe weather shift subtly. Researchers do not treat these simulations as perfect forecasts of any specific event. Instead, they are experiments, ways to probe how sensitive the atmosphere's most intense small-scale events are to broad, slow changes. The answers are nuanced, with regional differences and layers of uncertainty, but the underlying idea is steady. Local extremes cannot be separated from their global context. As the model runs quietly in a data center somewhere, the real atmosphere moves on. Night falls in one hemisphere, day dawns in another. Jet streams shift, fronts form and decay. Somewhere, a new supercell takes shape, its updraft tilting and stretching the air, its downdrafts carving out pools of cool air near the ground, its internal vortices forming and fading, mostly unnoticed except by a few instruments and a few curious minds. Here, in your own small corner of that atmosphere, the air is relatively still. The pressure is gently balanced, and your body is heavier than the air it displaces. You are anchored to the surface by gravity, surrounded by the same fluid that carries supercells and tornadoes elsewhere. But tonight, around you, it is calm. Let your thoughts move as slowly as the broad rotation of a mesocyclone. Let sharp worries diffuse, like vorticity spreading out in a stable layer. Each breath in is a small updraft. Each breath out is a gentle downdraft, rising, sinking, in a quiet, repeating cycle. The case of the invisible vortex is always ongoing for scientists and forecasters. But for you, tonight, it can end here. The storm structures can recede into the background. The equations can close their eyes, and you can rest. Good night.